Good morning. Today I'd like to start looking at how we'll program some of these simple integration methods that we've been talking about. I want to look at three in particular. I want to look at the left-hand rule, the right-hand rule, and the midpoint rule, which we have described previously. I want to write the code to do this. I want to try it out on a problem whose exact answer I know, and I want to compare the error in the three calculations. Naturally, since we have three methods and they're all based on single points within each subinterval, we would expect that the behaviors will be similar amongst the three methods. We'll see about that. Also, I want to introduce a new idea in terms of programming. I want to introduce the idea of a module. A module is a new type of program unit. We already know about main programs, functions, subroutines, and now we're going to have something called a module. If you go by textbooks, there's a very complicated definition for module. It is easier to actually show you one and show you what I'm going to use it for. So I've got a variety of programs that I've written here, and the first one is cleverly called 1.f90. Besides my main program, which is going to print out the number FP type, there's a new thing. There's a module. Just as with functions and subroutines, we start off with not function so and then end function, but now module so and end module. We can name the module whatever we like within reason. Coding statements, things like do loops and things like that, cannot appear by themselves inside of a module. As we'll see in a little bit, there's ways of getting around that though. What I can do in a module, all by itself with nothing else, is to declare things. So within this module, I'm going to declare fp type to be an integer parameter. And in fact, I'm setting that parameter equal to 8. Now, you may be thinking, isn't that a programming statement itself? Not really. This informs the compiler that the symbol FP type means 8 now and forever. So it's not really a programming statement in the same sense of a do loop or an if then else. After that, I say end module, and this is our first module. In program main, even before I say implicit none, I say use set fp. What this is going to do is, in the main program now, it knows about everything that's in set fp, which only consists of that single value fp type. So for our first effort at using a module to do something, I'm going to print out fp type in the main program. Now, if you look at it, this may look a little puzzling because of the implicit none, but the use set fp overrides that. Still, there are no variables defined in the main program except for fp type, which comes in through the module. I've already compiled that program. So if we run it, we see that fp type is 8. The next one I want to look at is excuse me, 1b. Within the module, you can make various specifications saying private : fp type is not a programming statement of the type we've had before. It's not a do loop or an if then else, but what this tells the computer is there's going to be this integer parameter whose value is 8 stored into a parameter named fp type, but program units outside of this module shouldn't see it. It should be invisible to them. So by saying private fp type, even though the main program is going to use set fp, it doesn't know about fp type. So if I try to compile this, it's probably going to complain. Well, it refuses to go along with me on this. In the implicit none in the main program that says there are no variables declared to be anything, and because of the private statement in the module, the main program doesn't know about FP type, even though it's using that module. Next, I want to look at .f90. Let me jump down to the bottom. No, maybe not. I may have to blah, 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 blah. Where is Mr. Main Program? There we are. So I'm going to have this program, which I'll just call main. It's going to use set FP. It's also going to use another module called integration methods. We'll talk about those in a moment. The reason that I wanted to introduce that module set FP is in case I wanted to change the value of the precision in my program, I'll do it through set FP. Anytime I'm going to have a floating point variable, I'm not going to be literal about it and say what the kind is. I'm going to use that module and say, for instance, real kind equals FP type AB. So later, if I wanted to change from double precision to quad precision, I only have to change that one line in that module. I declare the integer to be n. A is going to be 1, B is going to be 2. I'm going to use 100 subdivisions in the left end rule, the right end rule, and also the midpoint rule. We haven't looked at the code for that yet, though. My function is going to be described this way. Real kind equals FP type. Function f of x, I'm going to use set FP. I don't have to use integration methods here because this is the function that I'm going to integrate. It doesn't need to know about that other code. Implicit none. Real kind equals FP type intent n x. I'm going to integrate 1 over x from x equal 1 to x equal 2. The actual answer is the natural logarithm of 2. So by pushing all this stuff off into modules, that's my main program. That's all there is. I could have put the function f in a module, but it seemed to me, since the main program's purpose is to integrate function f, that they should be together in some way. Now, being simple-minded about this, at the moment, all of my code is in one huge file. This is actually the bottom of the file. All of the modules and stuff are up above it. So I'm going to page up until I get up to my modules. Firstly, Module set fp integer parameter f type equals 8. I'm doing G4tran on Linux today, so that means that that's double precision, 64 bits. I think in Silverfrost it would be 2. Later, if I want to do single precision, that is real, 32-bit typically, I'll change that 8 to a 4, and I think on Silverfrost it's 1. If my compiler supports the 80-bit version, we can do that. If the compiler supports 128 bits, we can do that too. I'm going to have another module. And do you remember when I said you couldn't have programming statements in the module on their own? That is true, but a module can contain other things. So my module is going to contain a function named write. It's a real kind equals fp type function. It's going to receive the number of subdivisions, the beginning of the interval, the end of the interval, and it's going to integrate this function f. At the moment, I'm being simple-minded about f. I'm assuming that the integrand that I'm looking at is literally called f. How do we say we're going to do this? Our spacing is b minus a divided by the number of subintervals we're going to have. It's bad form to divide by a floating point number by an integer just as is. We should say float or double, or generally speaking, real open parentheses n comma kind equals fp type. Then I'm going to go around in a loop and add up all of my function values. My function values are f at x0, f at x1, f at x2, out to f of xn. For the right-hand rule, we're supposed to take the right ends of the subintervals. So I'm going to be evaluating my function at x1, x2, x3, up to xn. I'm going to add up all of those function values, and then once I've added up those, I'll multiply it by delta x, and that's how we said we were going to do the right-hand rule. So after I say contains, this part, except about this floating point data type business, looks exactly like the kind of stuff that we've done before. So hopefully stepping up the level of abstraction just a little bit isn't going to throw anybody. After that, there's another function that my module contains. This function, it does exactly the same thing that write did, except instead of a plus I times delta x, it's a plus I minus 1 times delta x, converted into the appropriate floating point data type. I add up all those function values, which are the function values at the left ends of the subintervals, and then at the end, I multiply by the dx, and then I'm done. So again, except for the kind equals fp type thing, this is what we've done before. And the last one I'm going to look at today is the midpoint rule. I'm going to look at subintervals. Excuse me. I'm going to look at subintervals 1 through n, and I'm going to find the midpoint of them. So I'm not going to look at the left end, and I'm not going to look at the right end either. If it were just that, I would be doing the left end rule. But I want to add enough to this to put me exactly halfway across the subinterval. I want to add delta x over 2 to that. So that's why I add delta x over 2. We find the function values at the midpoints for subintervals number 1 through n, add them up, and after we do that, we multiply the sum by delta x, and that's how we said that we were going to do the midpoint rule. Going back down to the main program here, I set a to be 1, I set b to be 2. We're doing the integral from 1 to 2, 1 over x dx with 100 subdivisions. Because of the way I've coded this up, I just have to make references to left, right, and mid, and this will tell me my 3 approximations based on these 3 different ideas. Each of the ideas is based on a single data point, so we expect roughly similar behavior. Now, I've already compiled this to save time, so I'll just run it. The actual value of natural log of 2 is about 0.69 some odd, so these numbers are reasonable enough. Now that I've got it to this point, I can start doing some experiments. What I'm going to do next is I'm going to take what's in 2.f90 and I'm going to put it in a loop. So nothing has changed except the main program, so that's what I'm interested in here. The actual value of the integral is natural log of 2. Most computer languages, log is the natural log. What I'm going to do is I'm going to print out the left version, the right version, and the midpoint version of the approximate integral. I'm going to go around in a loop and do this 10 times. Whenever I've got a certain value of a loop index, I, I'm going to make n equal to 20 times I. So I'm going to be using n values that are 20, 40, 60, so on and so forth out to 200. I'm hoping to gain some sort of insight into the approximations. Aside from putting this do loop in, though, nothing has changed. As before, I've already compiled that, so I'll run it. And looking at this mass of numbers, it's difficult to see how good these approximations are. So I decided to do one other thing with this code. Besides printing out the values of the left end approximation, the right end approximation, and the midpoint approximation, I decided to print that stuff out and also print out the error. By error here, I mean the difference between my approximation and what the computer thinks natural log of 2 is. So once again, the only thing that's changed is the main program. Here is the same stuff that we were doing before. After that, I do 2 print statements to print blank lines to the screen to make it easier to read. And then after that, I have a very slightly altered version of that code. For I equal 1 to 10, I set n equal to 20 times I, but I'm not going to print out the values of the approximations left, right, and mid. I'm going to look at the error, the difference between the computer version of natural log 2 and the left-hand rule, the difference between the computer actual and the right-hand rule, and the difference that corresponds to that with the midpoint rule. Since every one of these methods is a method that is based on 1 point per subinterval, naturally we expect to see roughly similar results. So I've already compiled this, and being clever people, we know that the errors are all going to look roughly the same between the three methods here. That's what we expected, but that's not what happens. If you look at the errors that go with the left endpoint rule, they start off being roughly 10 to the negative 2 and end up being roughly 10 to the negative 3. If you look at the error that goes with the right end rule approximation, this is the middle column, starts off about 10 to the negative 2, goes down to about 10 to the negative 3. The left end error and the right end error are very similar to each other. This is what we expected to happen. But then there's that third column. For the midpoint rule, the error started off roughly 10 to the negative 5 and ended up being roughly 10 to the negative 7. This is 4 orders of magnitude better than the left and right error. And 4 orders of magnitude, 10 to the 4th power, is 10,000. It doesn't really take any more work to do the midpoint rule than it did the left end or the right end rule, and yet somehow it's coming up 10,000 times more accurate. This needs to be looked into, which I'll talk about in the second half of today's lecture, which will be some theory. One last thing before we turn the computer off for the day. Many times you don't want to have your entire program with all of its functions and subroutines and possibly even modules sitting around in one giant file. That's very inefficient. You can compile things in pieces if you want, and then later link them all together. Also, if you're more sophisticated about this sort of thing, you know that once you've got a bunch of code that's never going to change again, you can compile it into a library and then just link the library in. I'm going to do something simpler than that to finish the code discussion. I have chopped my source code up into a bunch of smaller files. I've got f.f90, I've got integration methods.f90, I've got main.f90, and I've got prec.f90, which obviously is precision. This file has nothing in it but the module that tells the computer what kind of floating point work to do. If you look at F, it has nothing in it but the function that we're looking at. If you look at main, it's got my main program in it and nothing else. And it doesn't take a rocket scientist to guess what the one remaining file that we haven't looked at yet has in it. The integration methods.f90 no doubt will have the integration methods in it. Module integration methods contains the function for the right end rule, the functions for the left end rule, the function for the midpoint rule, and that is all. If you wanted to become more sophisticated about the programming environment, you could have several files like this. If you're using a GUI, you could probably have new file in your GUI menus. I'm working from the command line here, so gfortran star.f90, and it compiled all of my different Fortran programs, functions, subroutines, or modules. It compiled them and stored them at 328. I got to reset that clock at 328 today. So the executable that we've created was created right now. It stored it in a.out because I didn't tell it to do any differently, and there we are. One parting shot before we go to look at why this is happening with the midpoint rule and how we can hopefully make it happen in other contexts. The real reason that I wanted to do the module thing with the floating point description is when we do our calculations, so far in the discussion, we've worried only about what you might call the calculus error. When we approximate functions with interpolating polynomials, there's a certain error associated with that. The error has only to do with things like the mean value theorem for intervals and so forth. No mention has ever been made of any kind of computer stuff. But when we actually compute, when we actually figure things out, we've got a problem. And that problem is there's also going to be rounding errors. So one thing I like to do is to run a program and see what kind of accuracy I'm getting, and then run it in a different precision and see if the accuracy changes a lot. If it does, that tells me that the rounding errors are a big threat to me, and I probably should sit down and think about what to do about that. If the order of magnitude of the error doesn't change, then that tells me the rounding errors play an insignificant role in the total error, and I can continue thinking in the way that we've been thinking, calculus and analysis wise, and not worry too much about the rounding errors. When you're looking at new algorithms, this is something you have to worry about. So remember how this goes. Left and right, the errors start off about 10 to the negative 2 and end up about 10 to the negative 3. Not much improvement. Midpoint rule, very roughly speaking, I'm seeing something times 10 to the negative 5 to something times 10 to the negative 7. What I want to do is I want to change this to single precision and run it again and see if that changes much. So what all do I have to change? Only one thing. My floating point data type. I don't want it to be 8 anymore. I want it to be 4. Recompile. Rerun. The errors start off about 10 to the negative 2 and end up being about 10 to the negative 3 for the left end and right end rule. The error for the midpoint rule starts off life being about 10 to the negative 5 and ends up being about 10 to the negative 7. The order of magnitude of these errors did not change when I went from double precision to single precision. This tells me that at least for this particular example, the rounding errors are not the big problem. The accuracy is going to be controlled by this calculus or analysis type error that we've been looking at by using the error term in the interpolating polynomial. Now, I don't want you to get the wrong idea. You don't have to code like this. Using modules can get very tricky, especially with scoping issues. Also, I haven't investigated what happens with silver frost in this situation, so you should feel free to code things in a simple way as we've done before, but you should at least be aware there's other ways of doing it. So I'm going to end the computer part of today's lecture, and then I got to figure out why is the midpoint method doing what it's doing, and how can I make that kind of thing happen more? We're going to have the right end rule, the left end rule, and the midpoint rule. The equations for the right end rule approximation is what you think it is. The error worked out to be negative 1/2 times f prime gamma times delta x multiplied by b minus a for some gamma between a and b. The left end rule, the approximation worked out to be this. We didn't explicitly work out the error term for the left end rule, but if you do it, it's extremely similar to that of the right end rule. So the right end rule on a subinterval uses this point, the left end rule uses this point, and the midpoint rule uses the point in the middle, which is going to cause some complications. But it turns out that these complications are the good kind. For our example, in our code, we used the integral from 1 to 2, 1 over x dx. The right and the left hand rule methods gave us very similar results in terms of the error, but the midpoint rule was much better. The way I'm going to think about this is this. I'm going to think about what would happen if I did basically the midpoint rule again, but I also had an extra point in the interval that I was interpolating at. Blah, 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 blah. So in subinterval number I, which goes from xi minus 1 to xi, we will have interpolation not only at the midpoint, m number I, but some other point, p number I, which is not the midpoint. We'll build up our approximation scheme based on interpolating polynomials, as we've done before. So now, in our x column, we have not only mi, but also pi. We'll have f of mi and f of pi, and the divided difference based on mi and pi is given by the usual formula. Note that since I'm saying that pi isn't the same point as mi, then I never get into division by zero trouble. Now, I'm interpolating at 2 points. My actual function value is the value at the midpoint times plus the usual approximation based only on xm plus the error term. So this is going to be the second derivative at alpha I over 2 factorial times x minus mi times x minus pi. The approximate value of the integral will be what I get when I approximate with integrals of things that I know. I know this number. I know these numbers. X minus something that I know. The approximation to the integral is going to be what I get when I integrate the sum of these first two terms. The error that I commit in this midpoint plus another point method is going to be this. It's going to be the integral of my interpolating polynomial error. So in a certain sense, this is very similar to what we've done before. The midpoint approximation to the integral on this one particular subinterval is f evaluated at the midpoint of that subinterval times delta x. What about this midpoint plus another point? We have to do some calculations here. At the moment, I'm not worried about the error in this. I'm just interested in what the approximation to the integral works out to be. So we will integrate not just a constant, but a linear function. So if you work all the calculus out, this works out to be this constant times x evaluated between xi minus 1 and xi. That gives you the usual midpoint approximation. And this term is going to be our improvement. It's going to be our improvement over what the midpoint method gave us. So we'll figure out what this quantity is, and then we'll know how much the midpoint rule changes when I take the midpoint rule only and also interpolate at an additional point. A remarkable thing happens. Mi is bigger than xi minus 1. The distance from mi to xi minus 1 is half of the width of the subinterval, delta x over 2. xi is bigger than mi, so xi minus mi is also delta x over 2. Of course, xi minus 1 minus mi is the negative of mi minus xi minus 1. So xi minus 1 minus mi is the negative of delta x over 2. So this quantity that showed up in our antiderivative term, this quantity, works out to be what you get when you square delta x over 2, square the negative of delta x over 2, and subtract those two things. That is to say, it's 0. What in the world does this mean? It means that the answer that comes out of the midpoint rule, this answer, and the answer that comes out of the midpoint rule plus this additional point pi, this quantity, they are the same thing. This was not obvious at the beginning, but it works out this way. Weirdly, the reason that this is true is because the midpoint is exactly halfway from one end and also halfway from the other end. That is the only reason that this is happening. It's happening because this difference works out to be 0. Well, if that's so, then the error in the midpoint rule is the same as the error in the midpoint rule plus this additional point pi. So the error in the midpoint rule is really, unexpectedly, the integral from xi minus 1 to xi of the second derivative of f evaluated at alpha I over 2 factorial times x minus mi times x minus pi. At first glance, it doesn't seem like there's much hope of evaluating that because it looks as though it depends on the pi. But that's not true. The error in the midpoint rule is going to be the same as in the error in the midpoint plus the additional point rule. This is the difference between the midpoint approximation and the actual value of the integral, this is the difference between the midpoint rule plus a point approximation and the true value of the interval. The midpoint rule has no pi in it, and yet this is equal to that. So despite appearances, this really can't depend on pi either. In the next homework set, I'll give you a little problem where you can easily convince yourself of that if you don't believe it. Once we come to believe that, we're in business. I can take the pi to be any number I want to, and it doesn't make any difference in the midpoint plus additional point rule. I could pick the pi to be down on one end of the interval or down on the other one. I could put it anywhere I want. Of course, I couldn't literally put the pi right at mi because I need 2 points to get this linear interpolating polynomial. What I'm going to do is, I'm not actually going to set the pi equal to mi. I'm going to take the limit as pi approaches mi. It also may not be obvious, but I can bring the limit inside. We'll talk about that in a homework problem. The error turns out to be the integral from xi minus 1 to xi of the second derivative of f evaluated at alpha I divided by 2 factorial times x minus m times x minus m. I've now got 2 factors of x minus m in my integral. We are now in a position to do something. I'm going to assume that the second derivative is continuous. X minus mi squared is non-negative because the square of a number is always non-negative. X minus mi squared never changes sign on the interval from xi minus 1 to xi, so I can use the mean value theorem for integrals to rewrite this integral as the second derivative of f evaluated at some beta I within subinterval number I divided by 2 factorial, which is 2, and then do the integral of the rest by itself. Antiderivative of x minus mi squared is 1/3 x minus mi cubed. I have to evaluate that between xi minus 1 and xi. So then I have to do some algebra. F double prime at beta I over 2 times 3 is 6. We'll have xi minus mi cubed minus xi minus 1 minus mi cubed. Xi minus mi, you'll remember, is delta x over 2. Xi minus 1 minus mi was negative delta x over 2. Now this time I'm cubing these things, so the negative signs don't go away. Here I'm going to have delta cubed over 8 minus the negative of delta cubed over 8. Which means when the dust finally settles, the error, the calculus error, in using the midpoint rule, which is the same as using the midpoint rule plus an extra point, turns out to be 1 over 24 times the second derivative of f at beta I times delta x cubed. And see, that's why this is doing this thing. Previously, the local error for things like the left end rule and the right end rule were delta x squared, and when we add up all the chunks, we lost a power on the delta x, causing it to become delta x to the first power. Here, the local error is of order delta x cubed. When we add up all the chunks, we lose one power on the delta x, but it's still delta x squared, not delta x. So, blah, 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 blah. So here we end up with 1 over 24 times, using our summation formula again, n times second derivative of f at gamma times delta x cubed, and the n is going to have the same effect that it had before. It's going to have the effect of lowering the power on the delta x by 1. So finally, factor out one of those three delta x's and write it as b minus a over n. You can use that to cancel the n out. The global calculus error in doing midpoint is 1 over 24 times the width of the interval times some value of the second derivative times the square of delta x. This is why the midpoint rule is better than left end rule and right end rule. And why did this happen? It sounds ridiculous to say, but this happened because the point that's the midpoint is in the middle. We like stuff where you have a bunch of points and one of them is in the middle and the others are symmetrically placed. That's going to be very convenient for us in several different applications. This is about all I wanted to say today. So in the next meeting and the next video, we're going to talk about some other methods. We're going to talk about the trapezoid rule. We'll talk about Simpson's rule. And now that we know what the deal is, we're going to be on the lookout for algorithms and methods for approximate intervals that work better than you would think they should. Until then, I hope everyone's having a good day, and I'll talk to you again real soon.